digression about MNIST in the paper. But if we talk about MNIST, which is easy to think about, if a number is a 3, it's a 3, right? That's what the ground truth tells you. But if the model thinks that that 3 looks more like a 7 or more like an 8 than a 5, there is information there compared to another 3 that looks more like a 5 than an 8. And so that's why they want to carry over this information. And that seems to, there's experiments, and when we'll get to the results, we'll talk about it, seems to be helping the generalization of the model. The interesting thing in that digression about MNIST, which is somewhere on page 2, I think, page 3, and I'm gonna come back to the Softmax bit in a minute. But they then tried to omit all of the examples of digit 3. So in the distillation process, they take the remainder of the function, remove all the 3's, train the model, the distilled model, on everything but the 3's, and see how well it does on 3's. And it turns out that because of this other information in the Softmax, it's able to learn what a 3 looks like. Which kind of serves as a supporting argument to why use the Softmax rather than the hard target. So I said I'd talk a little bit more about the Softmax, and one of the reasons is because of, where's it gone? Because of this, because of D, right? So the whole argument for this paper revolves a lot around the ability of the soft targets to carry more information than the hard ones. This is true in general, but there is one parameter in the Softmax that we tend to forget. I know that I spoke to a couple of people at nPlan, and we usually forget about the temperature in the Softmax. Because whenever you use the Softmax, we basically use t equals 1, right? Normally it's e to the zi divided by the sum over j of e to the z. And we forgot that division by t. Now what that division by t does is flatten the Softmax out. Yeah. Which means that the low valued probabilities become higher. Which means that the information is distributed along all the class labels rather than the single one that carries the output, right? So I think this is part of the trick of why it works, is because, and they go up to pretty high values in my opinion. I think they went up to 10. Yeah, right. In their experiments, they go up to 10, which is fairly interesting.
Excuse me, but wouldn't the question whether it's high or low depend on what is the average width of the activation? You could imagine a system where if the activation is 20 times as large as well on average, then a high temperature might not mean anything.
No, but in general, in general, what the high temperature will do is for the same values,
yeah,
right? It changes the exponential relationship of the proportion between the majority class and the others, right? So if you have outputs that look like this, then if you have a small temperature, you'll get very flat, very decided outputs from a Softmax. If you have a high temperature, it's basically changing this scale, right? So you can have it linear and just compress everything down. That's what you would do without Softmax, right? Divide by the sum. And what the Softmax does is make this scale logarithmic.
Yeah, you just think of the exponential curve. If you divide all the values by 10, those that are small will be...
Sure.
Yeah, they will, so when you do the exponential mapping, they will move less than those that are very large because they will fall a lot more quickly down the exponential. So you're flattening the soft.
But it must clearly depend on the temperature at which you trained the model, right?
It's a hyperparameter temperature.
Yeah.
But
this happens during training of the cumbersome model as well, right? So
yeah. But if you say if I train it 1 and distill at 6 would be the same if I train at 10 and distill at 6. Right?
Oh, that I don't know. They don't say it in the paper. My assumption is that they train and distill at the same temperatures. Sorry.
Oh no, I thought it was like important to note that like if you just take temperature 1, then like the soft targets basically become too similar to the ground truth labels. So basically, what you would be doing is you would be training the small model in the same way that you would be training it anyway.
Yeah.
So
Yeah.
that's why they increase the temperature.
Yeah.
Like,
Well,
like these-
there is one argument to make, which is they become similar to the ground truth labels, except for when the cumbersome model makes a mistake, right?
Okay.
And I think part of it is also being able to carry the mistakes. So if we think about like one-dimensional fitting, which is easy. It's the argument about, okay, this is obviously the lowest error function, and this is probably the best fit function, which has higher errors. If you carry the errors, you carry the regularization. But apart from that, yes, you're absolutely right. It looks way more, way harder, right? So the temperature is basically the softness of the softmax, I suppose.
It's also a prior, right? So to some extent you enforce a prior on your posterior. Because at high temperature it becomes perfectly flat.
Yeah,
And
yeah.
the temperature kind of says how much of your prior do you still put into the...
Yeah, exactly. Right, so it's a lot more undecided. I think that's part of the trick of why it works. Because it's basically you're spreading information, right? You can imagine like it's not going to be perfectly flat, and you're going to have more of that. Oh, this 3 looks more like an 8, or this 3 looks more like a 5 information floating around. Because the way it learns, and I hate math, so I'm not going to go through it, but it's also a small paragraph. It's basically doing, propagating the difference between two cross-entropy values. And basically, if you simplify it down, you're learning from the difference between cross-entropy of the cumbersome model, cross-entropy of the distilling. So I went over on this. The other interesting thing is, it's sneaked in here a little bit, but they did the experiment on NNet on everything, including training on everything, including the tester. I'm guessing the reason is because NNet is a fairly small data set and you don't care about being good on NNet anymore. It was basically a solved problem in 2015 as well. So it's more to prove the point that, yeah, okay, now it's worth doing some more.
Is there actually a deeper reason for using the cross entropy rather than KL divergence or something?
I don't know, to be honest. I think it's because it's easier to backprop. That'd be my assumption, but the paper doesn't say. You can try and email Hinton and ask him, right? If you ever get an answer.